have not mentioned? You mentioned ions and electrons and so on.
mention plasma.
So what is plasma? What is the role of plasma in nuclear fusion?
So plasma is a phase of matter or state of matter. So unfortunately, our schools don't. It's like, I'm not sure why this is the case, but all children learn the 3 phases of matter, right? So, and what does this mean? So we'll take like water as an example. So if it's cold, it's ice. It's in a solid phase, right? And then if you heat it up, it's the temperature that typically sets the phase. Although it's not only temperature. So you heat it up and you go to a liquid, and obviously it changes its physical properties because you can pour it and so forth, right? And then if you heat this up enough, it turns into a gas, and a gas behaves differently because there's a very sudden change in the density. Actually, that's what's happening. So it changes by about a factor of 10,000 in density from the liquid phase into when you make it into steam at atmospheric pressure. All very good. Except the problem is they forgot like what happens if you just keep elevating the temperature.
You don't want to give kids ideas. They're going to start experimenting, and they're going to start heating up the gas.
It's good to start doing anyway. So it turns out that once you get above, it's approximately 5 or 10,000 degrees Celsius, then you hit a new phase of matter. And actually, that's the phase of matter that is for pretty much all the temperatures that are above that as well too. And so what does that mean? So it actually changes phase. So it's a different state of matter. And the reason that it becomes a different state of matter is that it's hot enough that what happens is that the atoms that make up, remember, go back to Feynman, right? Everything's made up of these individual things, these atoms. But atoms can actually themselves be, which are made of nuclei, which contain the positive particles and the neutrons, and then the electrons, which are very, very light, very much less mass than the nucleus, and that surround us. This is what makes up an atom. So a plasma is what happens when you start pulling away enough of those electrons that they're free from the ions. So almost all the atoms that make up us up and this water and all that, the electrons are in tightly bound states, and basically they're extremely stable. Once you're at about 5,000 or 10,000 degrees, you start pulling off the electrons. And what this means is that now the medium that is there, its constituent particles mostly have net charge on them. So why does that matter? It's because now this means that the particles can interact through their electric charge. In some sense, they were when it was in the atom as well too. But now that they're free particles, this means that it fundamentally changes the behavior. It doesn't behave like a gas. It doesn't behave like a solid or a liquid. It behaves like a plasma, right? And so why is it disappointing that we don't speak about this? It's because 99% of the universe is in the plasma state. It's called stars. And in fact, our own sun, at the center of the sun is clearly a plasma. But actually the surface of the sun, which is around 5,500 Celsius, is also a plasma. Because it's hot enough that is that. In fact, the things that you see, sometimes you see these pictures from the surface of the sun, amazing, like satellite photographs of like those big arms of things and of light coming off of the surface of the sun and solar flares. Those are plasmas.
What are some interesting ways that this fourth state of matter is different than gas?
Let's go to how a gas works, right? So the reason a gas, and it goes back to Feynman's brilliance in saying that this is the most important concept. The reason actually solid, liquid, and gas phases work is because the nature of the interaction between the atoms changes. And so in a gas, you can think of this as being this room, and the things, although you can't see them, is that the molecules are flying around, but then with some frequency, they basically bounce into each other. Mm-hmm. And when they bounce into each other, they exchange momentum and energy around on this. And so it turns out that the probability and the distances and the scattering of what they do, it's those interactions that set the about how a gas behaves. Mm-hmm. So what do you mean by this? So for example, if I take an imaginary test particle of some kind, like I spray something into the air that's got a particular color. In fact, you can do it in liquids as well too. Like how it gradually will disperse away from you. This is fundamentally set because of the way that those particles are bouncing into each
The
other.
probabilities of those the particle bouncing.
The rate that they go at and the distance that they go at and so forth. So this was figured out by Einstein and others at the beginning of the Brownian motion, all these kinds of things. These were set up at the beginning of the last century, and it was really like this great revelation. Wow, this is why matter behaves the way that it does. Like, wow. But it's really like, and also in liquids and in solids, like what really matters is how you're interacting with your nearest neighbor.
Mm-hmm.
So you think about that one, the gas particles are basically going around until they actually hit into each other, though, they don't really exchange information. And it's the same in a liquid, you're kind of beside each other, but you can kind of move around. And in a solid, you're literally like stuck beside your neighbor. You can't move. Like, yeah. Plasmas are weird in the sense is that it's not like that. So, and it's because the particles have electric charge. This means that they can push against each other without actually being in close proximity to each other. That's not an infinitely true statement, which it's a little bit more technical. But basically, this means that you can start having action or exchange of information at a distance. And that's, in fact, the definition of a plasma, that it says these have a technical name. It's called a Coulomb collision. It just means that it's dictated by this force which is being pushed between the charged particles. Is that the definition of a plasma is a medium in which the collective behavior is dominated by these collisions at a distance. So you can imagine then this starts to give you some strange behaviors. Which I could quickly talk about. Like, for example, one of the most counterintuitive ones is as plasmas get more hot, as they get higher in temperature, then the collisions happen less frequently. Like what? That doesn't make any sense. When particles go faster, you think they would collide more often. But because the particles are interacting through their electric field, when they're going faster, they actually spend less time in the influential field of each other, and so they talk to each other less in an energy and momentum exchange point of view. Just one of the counterintuitive aspects of plasmas,
which is probably very relevant for nuclear fusion.
Yes, exactly.
So if I can try to summarize what a nuclear fusion reactor is supposed to do. So you have a couple of elements. What are usually the elements?
Usually deuterium and tritium, which are the heavy forms of hydrogen.
You have those and you start heating it. And then as you start heating it, I forgot the temperature you said, but it
about
becomes
100
plasma.
million. Yeah.
No, first it becomes...
First it becomes plasma. So it's a gas, and then it turns into a plasma at about 10,000 degrees.
And then so you have a bunch of electrons and ions flying around, and then you keep heating the thing.
Yep.
And I guess as you heat the thing, the ions hit each other rarer and rarer.
Yes.
So, oh man, that's not fun. So you have to keep heating it such that you have to keep hitting it until the probability of them colliding becomes reasonably high.
And so
also on top of that, and sorry to interrupt, you have to prevent them from hitting the walls of the reactor.
Yes, exactly.
Somehow.
So you asked about the definitions of the requirements for fusion. So the most famous one, or some sense the most intuitive one, is the temperature. And the reason for that is that you can make many, many kinds of plasmas that have zero fusion going on in them. And the reason for this is that the average, so you can make a plasma at around 10,000. In fact, if you come, by the way, you're welcome to come to our laboratory at the PSFC. I can show you a demonstration of a plasma that you can see with your eyes, and it's at about 10,000 degrees, and you can put your hand up beside it and all this, and it's like, and nothing, there's zero fusion going on.
So you have, sorry, what was the temperature of the plasma?
About 10,000 degrees.
You can stick your hand in?
Well, you can't stick your hand into it, but there's a glass tube. You can basically see this with your bare eye. Yeah. And you can put your hand on the glass tube because it's...
What's the color? Is it purple?
It's purple, yeah.
Blue and purple.
It's blue and purple. It is kind of beautiful. Plasmas are actually quite astonishing sometimes in their beauty. Actually, one of the most amazing forms of plasma is lightning, by the way, which is an instantaneous form of plasma that exists on Earth, but immediately goes away because everything else around it is at room temperature.
That's fascinating.
Yeah, so there's different requirements in this. So making a plasma takes about this, but at 10,000 degrees, even at 1,000,000 degrees, there's almost no probability of the fusion reactions occurring. And this is because while the charged particles can hit into each other. If you go back to the very beginning of this, remember I said, oh, these charged particles have to get to within distances which are like this size of a nucleus because of the strong nuclear force. Well, unfortunately, as the particles get closer, the repulsion that comes from the charge, the Coulomb force, increases like the inverse distance squared.
Oh no.
So as they get closer, they're pushing harder and harder apart. So then it gets a little bit more exotic, which maybe you'll like, though, that it turns out that people understood this at the beginning of the age of after Rutherford discovered the nucleus. It's like, oh yeah, it's like, how is this going to work, right? Because how do you get anything within these distances? It's like, require extraordinary energy, and it does. And in fact, when you look at those energies, they're very, very high. But it turns out quantum physics comes to the rescue, because the particles aren't actually just particles. They're also waves. This is the point of quantum, right? You can treat them both as waves and as particles. And it turns out if they get in close enough proximity to each other, then the particle pops through basically this energy barrier through an effect called quantum tunneling, which is really just the transposition of the fact that it's a wave so that it has a finite probability of this. It's this, by the way, you talk about like, do you have a hard time like conceptualizing this? This is one of them.
Quantum tunneling is one of them.
Yeah, this is like throwing a ping pong ball like at a piece of paper, and then every 100 of them just like magically show up on the other side of the paper without seemingly breaking the paper. I mean, to use a physical analogy.
And that phenomena is critical for the function of nuclear fusion.
Yes, for all kinds of fusion. So this is the reason why stars can work as well too. Like the stars would have to be much, much hotter actually to be able to. In fact, it's not clear that they would actually ignite. In fact, without this effect. Anyway, so we get to that. So this is why there's another requirement. It's not, so you must make a plasma, but you also must get it very hot in order for the reactions to have a significant